Hello and welcome to the TI Precision Labs video covering how a PCB trace acts as a waveguide. This is part of a larger series on PCB layout for good EMC. The series is specifically intended to cover mixed signal designs where the digital signals are less than 100 MHz and the clock rise times are greater than 1 nanosecond. This video looks at how return currents flow relative to the signal trace. The video describes the problem with ground plane discontinuities and also describes the best way to use vias to transition layers to minimize EMI. Let's get started by considering a PCB trace as a waveguide. This slide shows how a voltage step propagates down a PCB trace. In this example, we show a trace separated from a ground return plane by PC board dielectric material. As the signal propagates down the trace, a changing electric and magnetic field follow the wavefront. The electromagnetic wave propagates at a very fast rate of 1.8 times 10 to the 8th meters per second, whereas the actual conduction of electrons from the positive terminal to the negative terminal happens at a very slow rate of 0.01 meters per second. The key point here is that an electromagnetic wave is traveling through the PC board dielectric and is being guided by the trace on the top and the ground return plane on the bottom. Think about this waveguide as we step through today's material. Another way of looking at the same circuit is to consider the transmission line as a series of LC circuits. As the wavefront progresses down the PCB trace, the capacitor and inductor will charge to a steady state. An instantaneous current will be seen at the wavefront, but before and after the wavefront, the LC circuit will be at a steady state. This is really just another way of looking at the circuit shown in the last slide. Remember, this wavefront is traveling at a very fast rate, but the conduction current is moving slowly. We will look at this more closely in the next slide. This slide is meant to illustrate the difference between conduction current and displacement current. It shows a simple circuit with a voltage source, wire, and load. Conduction current is the travel of an electron from the positive terminal of the voltage source through the load to the negative terminal of the voltage source. This occurs at a very slow rate of 0.01 meters per second. The displacement current, on the other hand, travels at a very high rate of 141 times 10 to the 6th meters per second in FR4 PC board material. Think of the displacement current as a chain reaction of electron collisions starting at the source and traveling through the load back to the negative terminal of the source. As an analogy, consider a hose filled with water. When you turn on the water faucet, water will instantly come out of the other end of the hose. A chain reaction of water molecule collisions starts at the faucet, continues through the hose, and forces water out of its end. It may take some time for water from the faucet to reach the end of the hose, but water will squirt out of the hose the instant the faucet is turned on. Propagation of the electromagnetic waves and displacement current happen in a similar manner. The wavefront and displacement current move very quickly, but conduction current is very slow. Now let's discuss how return current flows in a PCB ground plane relative to the top layer signal trace for low frequency signals. The figure shown here is the top layer of a printed circuit board where the signal applied to the connector travels across the red trace on the top of the PCB to the DUT. For low frequency signals, the return current in the ground plane will spread across the board and follows the path of least resistance. In this case, low frequency means less than 100 kHz. For signals above 100 kHz, the return current flows directly beneath the signal trace. This is a very important and useful characteristic because it means that the return currents for high-frequency signals that are physically separated from each other will not mix. When the return current of two signals mix, this causes interference or crosstalk between the signals. Later, we will look at details on how PCB spacing impacts crosstalk. A silly analogy that helps explain how the wavefront beneath a signal trace changes its size is Mr EMI. Mr EMI is the wavefront between the top layer and the ground return plane. Mr EMI conforms to the size of this waveguide, so if the PCB trace is located close to a ground return plane, the size of the wavefront will be small. On the other hand, if the distance between the signal and the return plane is large, Mr EMI will grow large. Also, if there are gaps in the return path, Mr EMI will stretch to conform to the return path. Mr EMI is not your friend, so keep him as small as possible. I know this is a little silly, but I hope it will help you visualize how different PCB geometries will change the size of the wavefront. Now let's look at how a signal travels across a printed circuit board when the signal transitions with vias from the top to the bottom layer. Notice that this example uses an unusual stack-up with two internal ground planes. It turns out that this is a very good stack-up for EMI. We will cover this in detail later. Now we will look at a well-designed example using vias to transition layers, then we will look at a poorly designed example. Think of the signal layer and ground return paths as a waveguide where the wave travels. When the signal transitions from the top layer to the bottom layer, the ground return needs to transition from internal ground 1 to internal ground 2. It makes this transition using stitching vias as a vertical waveguide from the top to the bottom. The entire signal path in this example has a good continuous waveguide for the signal to travel. Now let's look at this circuit done the wrong way. Here we have the same circuit without stitching vias. In this case, the signal transitions from the top layer to the bottom layer without a vertical waveguide to contain the wavefront. Thus, you see RF emissions at the via transition point. You may be thinking that your system has only a 50 MHz clock, so how can we get high frequency emissions? Don't forget that the Fourier series of a square wave showed frequency content into the gigahertz, and the waveform rise time determines how much high frequency content you will have. The point of this slide is to emphasize the importance of stitching vias to provide a continuous waveguide for signals to transition between layers. Here's a 6-layer board example for a via transition from the top layer to the inner signal 1. This type of configuration has a nice advantage in that it does not require stitching vias. The ground return 1 inner plane acts as a return path for both the top layer and inner signal 1. It also acts as a vertical waveguide for the wavefront transitioning between layers. Note that because of the skin effect, return currents on top and bottom of the ground will not mix with each other. The skin effect is a phenomena where high-frequency currents only travel on the outside of conductors. One approach to connect internal ground planes together and also connecting top and bottom fill to ground is to use a distributed array of stitching vias. Many printed circuit board layout software programs provide an automatic method for creating this distributed array. The spacing between the vias can be set to be 1/10 of the wavelength for the maximum applied frequency. This slide shows a more common PC board stack-up where there's an internal ground plane as well as an internal power plane. This is a more common stack-up than the previous example with two ground planes. However, this can be a bit more challenging to achieve good EMI performance. It's interesting to note that the signal return current will flow in the closest adjacent plane. This is true regardless of whether the plane is either a power plane or a ground plane. So, in this example where the signal transitions from the top layer to the bottom layer, the return path needs to transition from ground 1 to the internal power plane. One problem here is that you cannot have a stitching via from power to ground as you would short the power to ground. Instead, the return current must transition through a stitching capacitor. In many cases, the stitching capacitor will simply be a decoupling capacitor closest to the via transitioning layers. In this case, you can see that the signal transitions from the top layer to the bottom layer with minimal RF emissions. This slide is the same design as the previous slide, but no stitching capacitors are used. When transitioning from the top layer to the bottom layer, there is no good path for the return current to transition from inner ground to inner power. This can lead to emissions when transitioning layers. This problem can be avoided through sufficient use of stitching or decoupling capacitors. One question you may ask is whether stitching capacitors are as effective as stitching vias for connecting two planes together. The short answer is that stitching capacitors will generally not be as effective at high frequencies as stitching vias. The reason is that the stitching capacitor will require two vias and a capacitor. The capacitor and both vias will have inductance that will limit the effectiveness of this AC connection between the two planes. The stitching via will also have inductance, but it will be less than the stitching capacitor and its two associated vias. Also, the stitching via are small and virtually free of cost, whereas the capacitor will take up PCB space and add cost and complexity to the design. However, in general, the stitching capacitors are often decoupling capacitors, which are required in any case. Some PCB designers will use a distributed array of stitching capacitors or decoupling capacitors similar to the via array discussed previously. I think it makes more sense to strategically locate the capacitors where they are needed. We will focus on the importance of local decoupling later in this presentation. Previously, we mentioned that for high-frequency signals, the return current will travel on the ground plane directly beneath the trace. This requires a continuous ground plane. If there is a slot or discontinuity in the return path, the ground current will have to find a different path. This creates RF emissions. The example shown here will emit RF signals from the board as well as interfere with the victim trace shown. Emissions caused by slots in the PCB return path can be very significant, and this is one of the leading causes for system-level EMC problems. Of course, the best practice is to avoid a slot in the ground plane. In some cases, this may not be practical. One way to minimize the impact of the discontinuity in the return path is to use a stitching capacitor or a ground bridge adjacent to the trace. In this example, you can see that the return current transitions from the ground plane to the top layer stitching capacitors to travel over the gap in the ground plane. That concludes this video. Thanks for watching. Please try the quiz to check your understanding of this video's content. Question 1. In the PCB layout below, a signal trace is driven above 5 volt and 3.3 volt power planes. Are there any potential EMI issues with this design? The correct answer is B. The return current will flow in the adjacent power planes, but the power plane is split, so high-frequency return current will not be able to stay under the signal trace, causing emissions. The animated wavefront shows the return current has no obvious path, so RF emissions happen, and the return current spreads across wide regions of the board. Question 2. In the PC board layout below, what are some approaches that could be used to improve EMI performance? The correct answer is D, all of the above. Probably the easiest solution is to simply reroute the trace so that the return current has a continuous path on the 3.3 volt plane. Another approach is to make sure that the signal trace is always adjacent to a solid ground plane, so changing the stack up so that ground is beneath the top signal will work. Finally, providing a connection with a stitching capacitor between the planes is a possible approach to connect the two planes from an AC perspective. Question 3. For the two circuit boards shown, an analog signal trace is placed near a digital signal trace. The layout is the same for both PCBs. The only difference is the PCB thickness. Which layout will minimize the interference between the digital and the analog? The correct answer is B, design 2. The thick dielectric provides room for the return current to spread out. Let's take a look at the Mr EMI analogy on the next slide. Here you can see that Mr EMI has more room to spread out for the thicker dielectric. Thus, the fields for design 1 overlap, but on design 2 the fields are much smaller and are separate from each other. This means that the crosstalk is lower for design 2 than 1.